In mathematical physics, the most profound theoretical leaps occur when two highly tested mathematical frameworks yield contradictory boundary conditions. General relativity defines the macroscopic geometry of spacetime. It predicts that a high enough concentration of mass will trigger a complete gravitational collapse. Here, a 3D spacetime manifold warps into a deep gravity well. The red circular boundary is the event horizon. According to the no-hair theorem, matter crossing this threshold loses its complexity, leaving the black hole characterized entirely by mass, charge, and angular momentum. Any complex physical state that crosses this boundary is causally disconnected from the outside universe. This model of absolute gravitational finality arises directly from the field equations of Albert Einstein. Classically, black holes act as absolute information sinks, erasing the history and structure of the matter that formed them. But shifting the framework from classical gravity to the microscopic rules of quantum mechanics reveals a massive contradiction. The problem is unitarity, the quantum principle that information is never destroyed. In this Bloch sphere, a quantum state evolves deterministically, rotating to a precise new coordinate. Because this is deterministic, information is conserved. Knowing a system's exact state now allows you to perfectly reverse its path and calculate its past. This logic leads to a catastrophic thought experiment, dropping a precise quantum state into a classical black hole. General relativity dictates the state is gone. Quantum mechanics dictates the state must still exist somewhere in the universe's mathematical matrix. One of our foundational theories must be mathematically flawed. The universe cannot simultaneously obey geometric finality and quantum determinism. Stephen Hawking forced this clash into the open by calculating quantum fluctuations directly on the boundary of an event horizon. Quantum field theory shows that empty space is boiling with virtual particle-antiparticle pairs that constantly pop into existence and annihilate. This diagram illustrates Hawking's realization. When these pairs form exactly on the event horizon, gravity can pull one particle below the boundary, allowing the other to escape. These escaping particles become real thermal radiation emitted into the universe, a phenomenon known as Hawking radiation. Since the escaping particle carries positive energy away, the infalling particle must have negative energy, which subtracts from the black hole's total mass. This redefines the black hole from a static void into a dynamic object that interacts with the universe. Hawking radiation proves that black holes are active thermodynamic entities, firmly embedded in the universe's life cycle. This continuous emission of thermal energy into the surrounding cosmos ultimately leads to a continuous, unavoidable loss of the black hole's total mass. As the black hole shrinks, it gets hotter and radiates energy at an accelerating rate. The end point of this process is complete evaporation, where the black hole vanishes entirely in a final flash of energy. The paradox centers on the quality of the radiation left behind, which is strictly thermal. This diagram compares highly structured infalling matter to the resulting radiation. Pure thermal radiation is mathematically featureless. It is essentially randomized noise that carries zero complex data. Structured objects like stars and data fall in, but only randomized noise comes out. Evaporation leaves behind energy, but the specific quantum history of whatever formed the black hole is effectively scrubbed from existence. This crisis is the black hole information paradox. This diagram outlines the contradiction. The initial highly ordered quantum state does not equal the final, randomized thermal radiation matrix. Because the equation fails to balance, quantum information has been permanently destroyed. This destruction violates the Liouville theorem and the core principles of quantum mechanics. If unitarity fails inside a black hole, the mathematical predictability of the entire universe collapses. For decades, physicists were trapped in a choice between abandoning Einstein's gravity or abandoning quantum mechanics. The information paradox exposes a breakdown in the rules of the universe. Resolving it requires a theory reconciling the finality of gravity with the conservation of quantum states. Modern physics attempts to rescue unitarity by shifting the focus away from the center of the black hole. Instead of looking at the singularity at the center, physicists look closely at the two-dimensional surface of the event horizon. This is the horizon encoding hypothesis. As matter falls toward the black hole, Its quantum information is scrambled and mathematically flattened onto the horizon. This diagram shows a 3D object flattened onto a 2D grid plane. The physical matter may pass through the boundary, but its quantum blueprint is caught in the geometric webbing of the horizon. Mathematically, the event horizon functions as a high-density, two-dimensional quantum storage drive. Horizon encoding provides a mechanism for information to escape during evaporation. Hopping radiation is generated at the horizon, where it interacts with the encoded quantum blueprint. This diagram tracks the radiation arrows passing through the grid. The outgoing energy acts as a carrier wave, subtly imprinted with the quantum information before it flies into the void. The black hole evaporates, the radiation escapes, and unitarity is preserved. If the description of a three-dimensional volume can be fully contained on its two-dimensional boundary, the third dimension is effectively a redundant projection of that surface data. This underpins the holographic principle. It suggests that the 3D reality we experience is an emergent projection, a construct generated by the interactions of quantum information on a distant boundary. The information paradox forces a realization that spacetime is not a fundamental background. It is a geometric manifestation of the universe's underlying effort to conserve information.